Today, we're solving the two-dimensional Schrodinger equation based off these two Reddit posts. And I've already made a video on the one-dimensional Schrodinger equation. So if you haven't watched that, please give that a watch because there's techniques we'll be using in this video that we'll need from that video. And by the way, the two-dimensional is so much cooler too. I mean, look at this solution to the 2D infinite circular well. Wait, hold up. Do you guys see something? Who knew that was part of the Schrodinger solution? What can I say? Alright, so there's a lot of heavy math in this video, so I'm going to start with a little bit of math to sort of get you used to how we're going to implement this in Python. Alright, so we'll start with a little recap of one dimension. So here, for example, is a continuous wave function you might see in one dimension. It goes from x equals 0 to x equals L. And these are just arbitrary values. Now, the goal of solving the Schrodinger equation in one dimension is to find functions psi and values e that work with this equation. And there's only certain functions and certain values of e that work. And when I find those certain values of e, it tells me about the energies of my system. And when I find psi, it tells me about the energy eigenstates, or in other words, when you measure the system, what the states take at a certain energy. And so this is the equation obviously written here again, and you use some sort of analytical technique to solve this. You can make this discrete as follows. Your wave function written here, the boundary condition that we're going to assume here is that psi is 0 at x and L. We have to assume that numerically for the method we're going to use. Then there's all these points in the middle, psi 1 to psi n, right? And you could, like, these make up a vector because there's finitely many points. And there's a few things we need to rewrite the Schrodinger equation. We have this approximation of the second derivative that I've used in other videos as well, expressed here like this. And at every point I, right, we're also going to have a value of the potential that we have. So with these two things, we plug these into the Schrodinger equation. We set h bar equal to 1, which is common in physics. And this becomes our new Schrodinger equation, written like this. So you have a constant times psi I minus 1, psi I minus 1, and this equals e, and I need to write a psi I here as well. And this is a system of linear equations, right? With my psi I as a vector, and it can be expressed as a matrix like this. And so what I'm going to do is I'm going to let di equal this value here, because this will be on the main diagonal. And you'll see if I take any value of psi here and I multiply by the row, I will get this. So all these equations for each value of I are written in this matrix form. And from this we can find eigenvalues and eigenvectors. Now this becomes a little bit more complicated in two dimensions when our values are on a grid like this. And on a grid, right, 0 on the outside, we have to assume 0 at the boundary. And our state is represented by a matrix, right? Where here you go across x, right? X being this side here, and across columns is going across y. So each row has n points in x and then n down in y. And the question is, well, we have this matrix, but we want to do stuff with a vector because it's the vector that will allow us to do, find the eigenvalues of some sort of matrix, right? The easiest way to turn this into a vector is to take each row of this and stack them up. So here I take this row, I stack it here. This row, I stack it underneath. And then all the way down to the bottom row, and I stack that underneath. I have n rows. Each row is of length n. So the total size of my vector is n squared. That makes sense because obviously the size of this is area of size n squared. So we're taking this and we're squishing it down into a vector. And it contains all the same information. As a really easy example, you have a 3x3 grid. Here's your size. Remember that there would be points on the outside all equal to 0, right? Anyways, and this is our vector that we get when we squish it down. And this 3x3 case is important because we're going to use it to understand what we need to do to solve this in 2D. Because constructing the Hamiltonian in this case is more difficult. So the question is, what does the second derivative of x look like? Well, we know in one dimension, if I draw my plot like this, right? And I have my boundary conditions here. And remember, I'm only solving for the 3 points on the inside. And this would be psi 1, psi 2, psi 3. that our matrix for the second derivative looks like this, and you can check this. If these are always equal to 0, then this is always the second derivative, 1 over delta x squared, and you have these things here. And I'm going to define this as dx, right? Now, the question is, how do you do this in 2 dimensions when you have x and y points, right? Say you have 3 points in x and 3 points in y. Well, I'm going to have to introduce you to the Schrodinger product, and it's a really simple concept. It's written as I times with a circle around it, dx is equal to 1 over delta x squared, and every element in I, the first thing written here, I multiply by the matrix D. So here's my D in this column. These aren't zeros, these are D's, and everything else is 0. And so it's like 1, remember I is 1, 1, 1, so I multiply by D, by D, by D. And this is technically 0 times D, but I don't want to write that out everywhere. And so then I expand the matrix, because D is, of course, 3 by 3. So when I insert these matrices here, like this. And now I have something that I can multiply by a vector. And you might think, well, okay, you've talked about this, but why does this work? The way that you need to convince yourself that this works is take this 3 by 3 vector, right? Plug it into this matrix, and you'll see that it returns the derivative, the second derivative at every location. And it works specifically because these points on the outside are 0, right? And you'll see like, oh, it looks weird because there's 1, 1, and then there's a point 0 here, and then there's 1s and 0s. It looks weird. Like you think that the main diagonal would be full. It's not, right? And that's important. And you'll see why that's the case when you take this matrix and you realize that, you know, it's 0, it's surrounded by zeros on the outside. So this would be like your 2-dimensional grid. You take that, you plug it in, and you'll get y. This is the derivative in x. Derivative in y is slightly different, the second derivative. It's dy with this times I. So here I take all the elements of d, which are written here, and I multiply them by I. So minus 2i, 1i, 1i, and I realize there's a mistake here. As a matter of fact, this should be a 1i here. And I plug this in, and I get 1 over delta y squared, and each one of these blocks is just the element 2. So this is like minus 2, minus 2, minus 2, because this is just the identity matrix multiplied by minus 2. Same here, 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 and here. This matrix looks a lot more complicated because here I have minus 2 on the diagonal, but here I'm spaced out from the other diagonal with these 1s. And you might think, well, why this spacing? Where does that come from? Well, that has to do with this, right? Suppose I want to take the y derivative. To take the y derivative, I consider this point, and I have to consider the points up and down. So in my vector here with psi 2, 2, I have to go all the way to psi 1, 2, and then all the way to psi 3, 2. And in terms of the matrix, that means I need spacing. It means I need a few points to get to 1. So here I have minus 2, 0, 0, 1. So what that means is it skips 0, 0, 1, right? 0, 0, 1. You have that spacing, 2 zeros in each column. Plug in the vector, and you'll see exactly what I mean. It's non-intuitive, but it works. So that means we can represent our operator here as I times D plus D times I. And this is equal to D plus D, where this plus is defined as the Schrodinger sum. And the Schrodinger sum is defined as follows. A plus B is A times I plus I times B. So we can write our Hamiltonian with this symbol involved. And so I had an I here instead of a D. So here we have our continuous Schrodinger equation that we then turn into this discrete form where we have minus h bar squared over 2m. We're going to use h bar is equal to 1, of course. Here we have our Schrodinger sum plus vi. Now, vi is as follows. You have your sort of grid of v's that correspond to your grid of wave functions as well. And basically what this vi represents is I take v, all these elements, and I stretch them out like I do with the wave function, and I just put them on the main diagonal here, right, like this. So that's what vi represents. This whole thing is an n squared by n squared matrix. Psi is an n squared vector, and e is a constant size an n squared vector. And so we can solve this equation in Python. Let's do it. All right, so we can code this in Python now. There's a number of packages I'm importing today. Specifically important one is the scipy.sparse linear algebra library. This deals with big matrices where there's lots of zeros, which is what we'll be dealing with today. You don't need this line here. This is for me making nice plots. So first let's start making a mesh grid of x and y, because remember our wave function is defined on a grid. So we're going to use a 150 by 150 grid. And we're just going to make a mesh grid. I'm going to call it x, y is equal to numpy mesh grid. And we'll go np.linspace. And I'm just going to go between 0 and 1. I know there's L, but... and I'm going to go dtype equals float. And I'll do this. Repeat it twice for x and y. And I didn't put an E. And so the way a mesh grid works, of course, is it's a 2D grid where every point tells you, like the x tells you where you are in x, and the y grid tells you where you are in y. That's why x is the same along the column, because wherever you're here, you're always at the same x point. And for the y one, it's the same across rows, because you're always, on the top row, you're always at the same y position. Of course, that's how a mesh grid works. So our equation we need to solve looks like this. D is the matrix. I forget how I defined it in the notes, but the way we're going to use it here is D has -2 on the main diagonal and 1 on the 2 neighboring diagonals. So that's important. That's how D is defined. V is the potential, of course, and then the way that it's written, you'll note I have m delta x squared v. So when we define the potential function, we're actually writing m delta x squared v, right? The potential, that's our units, essentially. When we write get potential, it returns this. So let's make a potential. And we'll start with something simple. We'll take an x, y, and right now I just want to do the infinite square well. So it's just going to return 0 times x. That's a simple one. And let's, so it's just always 0. And I'm going to say v is equal to get potential x, y, capital X. So now we have our potential, and now we need to construct this. And this is going to be using those Kronecker sums and Kronecker products I was talking about. So we'll break it down. We'll say t is equal to -1/2 d Kronecker sum d, and mu is like this. So let's define our things. We're going to start with defining diagonals, because everything is written in terms of these diagonals. Remember that d is the it's the one-dimensional analog, so it's got -2s and then 1s and 1s. So let's create a diagonal. It'll be just 1s repeated n times. So this is just an array of repeated 1s, and there's n of them. We're going to create 3 diagonals. Remember that D has -2 and 1 and 1, so we'll create those. So you'll note that diags, the first is the lower than the main diagonal of all -2s here, and then 1s like that. So those are our diagonals. And we can create our matrix D as follows. Remember that D has -2, 1, 1, and it's really easy to create using this method. So I go sparse.sp.ags. It takes in the diagonals. Okay, so what's going on here? There's 3 diagonals and there's 3 points here. It says this first diagonal, which is all 1s, will be put -1. So there's the main diagonal that's indexed at 0. -1 means 1 below the main diagonal of this matrix in this sp.diags method. 0 means put it on the main diagonal, and 1 means off 1 above the main diagonal. So I put all 1s, 1 below the main diagonal, on -2s at 0, and then diag again at 1. So that's the way that this is written here. And it's n by n. That's the matrix. So that constructs D. And D is now a sparse matrix, so we can't see it. It's conserved. It's 150 by 150. And then it's easy to construct T. T is just -1/2 times, and there's an easy function for this, Kronecker sum. Look how easy that is. Super difficult to do on paper, but easily done here. And we'll construct U as well. Remember that mu is this V, and V needs to be stretched out along that diagonal, like I talked about during the notes. V is like a 2D grid, but we stretch it out like we do with the wave function, and we put it on the main diagonal of a matrix. So I need to go v.reshape. It gets reshaped into an n squared. Remember that V is a grid, and now it's reshaped into an n squared vector. And we're going to put that, what this says here is I'm going to put this on the main diagonal of a matrix. So that's mu, and then H is equal to T plus mu. And I need to use sparse. So now I have h, and h is 22,000 by 22,000. Remember, it's n squared by n squared. This is why we need to use these sparse matrices. And it's actually really simple now to solve this equation. I can just say eigenvalues, vectors equals, we're going to use this eig_sh method. We feed it in the Hamiltonian, k equals 10, and which equals Sm. This means only look at the smallest, S for smallest. We're looking at the smallest eigenvectors, or sorry, eigenvalues of this equation. So I go like this, it runs very quickly, and I can print the eigenvalues here. And we'll look into these a little bit later. For now, I want to sort of plot some of the eigen vectors though, because they're kind of cool to look at. So first I'm going to write a function that gets the eigenvector. First of all, I'll write this and then I'll explain why it's written the way it is. We're going to return eigenvectors.t. We're going to take the nth and we're going to reshape it. So what's going on here? N tells me the nth highest eigenvector, so there's obviously the ground state wave function, and n is like the what level up wave function you're at. The way that eigenvectors is returned is it returns like this. I have to, if I transpose this matrix, then the first row is my first eigenvector. But this row is n squared long, and I want to put this back into the 2D grid so I can plot it, right? Because we have a 2D geometry here. So then I say I'll take my like 0th, for example, and that gives me my first one. And then I reshape it. So here it's like n, and then I reshape it back to be a 2D grid. And then I can plot these. So I'll make a quick contour plot, plot.contour f. Let's make sure the grid is square too. So plot.figure. We'll go 9 by 9 grid, and we'll just plot this. So let's plot the, rather than the eigenvector, we'll plot the probability density function, which is it squared. So x, y, and we'll go get e, and let's just plot the first one. We'll use 20 contour levels. And this is like about what you'd expect for the 2D square well. This is the first energy level. And I can plot the first, and the second, and the third. Sometimes the wave functions are a little strange. Oh, and I need to square them, of course. I'm expecting the probability density, so this is what you see here. And sometimes, like, these technically should be, vertical from each other. Sometimes it rotates them a little bit. This is a numerical issue. But it turns out the energies, which are the most important things, aren't really affected by this. So sometimes it gets these like rotated a little bit, but it's not a big deal. Especially the first two. The rest are usually good. You have the 4 here. That's what you expect exactly. And you have something that looks like this, the 3 sign. So that's the next one. So usually, sometimes those first, the second and third are a little strange, those eigenfunctions. Here's some code here I wrote for making an animation. I don't really want to go through it. Here I'm plotting the 5th one. Basically, instead of looking at it as contours, you actually make a surface plot, and then it rotates it around as a GIF, so you can sort of see the different angles that are going on and look at the surface. And of course, it's proportional to the probability density function. And we have something proportional, yeah. And I use this color map here. And basically, the way I do this is by rotating the azimuthal angle, right? So you get like this sort of switch like this, and it looks like it's finished. And you get this beautiful looking plot here where you can see this. So this is just sort of a bonus, not super important. What's probably the most important here is actually the energies as opposed to the eigenfunctions. Because for quantum systems, you're usually really interested in the energies. So let's look at those. So the first thing to note is that for the infinite square well, the energies are proportional to nx squared plus ny squared, and the first energy is at nx equals 1 and ny equals 1. That means that alpha, we could say, is equal to eigenvectors 0 divided by 2. because this is 1, 1, we divide here, and that gives us alpha. And then we can find our normalized eigenvectors. So E divided by alpha is equal to values divided by, sorry, this shouldn't be eigenvectors, this is eigenvalues. And then I go eigenvalues divided by alpha. And this, if I divide by alpha, I get nx squared plus ny squared, or I should get something like that, right? So if I plot.scatter these, and first I need to make, actually, let's make a dummy array just so I can plot.scatter these. This is equal to mp.arrange. We'll go 0, length of eigenvalues, and I'll go 1. So this is just a dummy, so we can scatter plot this. I'll go this, and then E divided by alpha here. And you can see that, sure enough, we have, this is our lowest energy, which is at 2. That's n1 squared plus n1, or 1 squared plus 1 squared. This is at 5, so 1 squared plus 2 squared, and there's 2 of them, because we can have nx equals 1 and y equals 2, or the opposite, vice versa. And you see that there's these degeneracies, and we can actually plot lines to show where they should theoretically be. So I can go nx squared plus ny squared. Let's make them red. I'll go 4nx in range 1, 4. Let's go 5. 4ny in range 1, 5. So this tells us a little bit about our spectrum of the system. And there's an invalid syntax here because I forgot to add these together. And so you can see that our energies lies perfectly on these lines, which is what is expected. And these lines up here, but I haven't solved for energies that high. I only found the first 10 eigenvectors when I use this method. So of course the infinite square well is a standard example. You don't need to do it numerically. So let's do something a little bit more interesting. I'm going to define a more interesting potential. And I'm going to return a little Gaussian bump off-centered. So I'll go x minus 0.3 squared divided by 2 sigma squared. So this tells us that it's centered at 0.3 and sigma is 0.1. And I'll do the same for y. Whoops. So here's my little Gaussian bump. And I'll just do a little plot.im show of this for you. And you can see that sure enough, it's a little exponential bump located off-centered here. Imshow reverses it, so yeah, that's all right. And then I can solve this really quick. And now this is sort of neat. This is the 4th one, so let's look at the 0th one. So the bump is right here. I know imshow showed it up here, but imshow flops the y-axis. So really on this scale, it's down here. So it wants to stay away from it. And then I can plot my first one, and you get 2 bumps. And I plot my second one, and you get these 3. And I could keep going, and you see how it kind of separates like this away from this bump. Of course, it doesn't want to be near the bump. And I'm not going to animate this one. And as for the energies, I'll get rid of these lines because these are only for the 2D. Well, and you can see that they go up, but they're kind of jagged, and it's not something that you would easily know how to predict. Anyways, what I think would be cool is if you guys took this code and you found out some potential and found something that looked really cool, and try to play around with different potentials. There's a lot of potential in this problem. So anyways, I hope you enjoyed this video. Please like and subscribe if you enjoyed, and I'll see you next time.